Hi, so today we're going to talk about the transfer of electrons. So the transfer of electrons. So why is it that metals are usually found locked up in ionic compounds or in other ore deposits? Why are outcrops of pure metals so rare? If we recall from Chapter 1, it is that most stable arrangements for metals is to have the outer levels resemble those of noble gases. This stability can be achieved by metal combining with a non-metal. Silver atoms, for example, can combine with sulfur atoms under a variety of conditions, as extreme as the inside of a volcano or as ordinary as a silver spoon sitting on a kitchen counter. So as shown in this next picture, in both cases, this process involves a transfer of electrons from a metal to a non-metal. So here we say that the metal is made up of positively charged particles within a sea of free-floating electrons. So we talked about this before as our metal bonds. So we've seen this before, okay? Now occasionally some of the free-floating electrons are lost to other atoms in the environment. The loss of these electrons turn the metal atoms into positively charged ions. So as we can see here, we've got the silver solid is going to go to the silver ion plus 1 electron. This is the free-floating one, okay? That's the one that leaves. So the positive metal ions are then attracted to the negative ions that have received the electron. This ionic compound forms a crystal structure that is the black tarnish that we see on the silver spoon, in this case with the sulfur. Now, oxidization is the loss of electrons. So when an atom loses electrons, it undergoes a process called oxidization. Originally, oxidization meant any reaction involving oxygen, but the term has been expanded to include any chemical process in which one substance transfers electrons to another substance. So there the definition says, again, a chemical process involving the loss of electrons, okay? That's the most important part there. Now we have examples here of oxidization reactions. So neutral atoms lose electrons and become positively charged ions. So oxidization, there we go. Oxidization produces positively charged ions known as cations, okay? Produces positively charged ions or cations and electrons, okay? So as we see here, we've got the metal ion goes to the metal cation and 2 electrons. Now negatively charged ions lose electrons to become neutral atoms. So again, this is negatively charged ions, okay? Positively charged ions lose electrons to become even more positively charged, okay? So in this case we've got positive metal ion becomes a more positive metal. So oxidation, I should say, produces positively charged ions, cations, and electrons. This is only from neutral atoms, okay? If we've got anions, turn neutral, and cations turn more positive. Okay? So reduction, though, this is the gain of electrons. Okay? So in that previous figure, the silver ions gain electrons to form pure silver. So when atoms gain electrons, they undergo a process called reduction. At first glance, this seems to have things backwards. How can a gain of electrons be a reduction? Well, historically, the name reduction comes from the metal refining industry, where the application of this process involves reducing very large amounts of ore into smaller amounts of pure metal. As the following examples indicate, the term reduction has been expanded to include any reaction in which there is a gain of electrons. Okay, so the opposite of oxidization. So here's our example of reducing reactions. Here, if I've got, a neutral atom becomes reduced, forming anions. Okay. Again, here we've got our nonmetal molecule. We're going to add 2 electrons to it, and then we get our nonmetal negative ion. Positively charged ions gain electrons to become neutral atoms. Okay, so if we've got a positive cation, reduces to a neutral atom. Okay, and then positively charged ions gain electrons to become less positively charged. Okay, so positive ions are reduced to less positive ions. See, sadder ions. Okay. So we've got some options here. Now, hints for keeping it all straight. Now we can use the following hints to remember the definitions and circumstances of oxidation and reduction reactions. And what they say here is oil rig. Okay, that's their little acronym. So these 2 words are a memory device to help you remember the definition. Oxidation, O, is the loss of electrons, and reduction is the gain of electrons. So the following may help you identify processes of oxidation and reduction. So this is a really good thing here just to show, something that's negative becomes neutral, something that's neutral becomes more positive in an oxidation reaction, and the reverse is also true. So something that is positive becomes neutral, something that's neutral becomes negative in a reduction reaction. Okay, we can also think of many other things to come up with that. So single replacement reactions. Refining copper ore to produce pure copper metal can be made in the useful products involving reduction. Clearly, reduction is a chemical process that involves the gain of electrons. Another substance must lose the electrons. So in this activity, at the beginning of the chapter, we will have observed some chemical reactions. And so now we're going to determine whether oxidation or reduction has occurred. So, our first problem here says a silver nitrate solution reacts with solid zinc to produce zinc nitrate or a zinc nitrate solution and solid silver. So first we have to write a balanced chemical equation that describes this reaction. Then we need to carefully examine each substance before and after the reaction to determine whether oxidation or reduction have occurred. So it says use half reactions here to support our answers. Okay, so let's look at a solution here. So first thing we have to write a balanced equation. So it says here that silver nitrate, which is AgNO3, this is aqueous because it's a solution, will be added to solid zinc. Will be converted to zinc nitrate solution. So NO3, 2. This is aqueous because it's a solution, plus solid silver. Okay, so let's see here. What is not in balance? Well, To begin with, this is not in balance. Got 2 nitrates here. So that means that I will need 2 nitrates here. If I've got 2 nitrates here, then I need 2 silvers. So I need 2 silvers over here. Now if we look here for B, let's look at the silver. Okay, so before the reaction, okay, it is in an ionic compound, which means that it is the cation, okay, in solution. But after the reaction, okay, oh, sorry, this should be Ag, is a solid silver metal. Okay, so with no charge. So since the silver started as a silver ion and became a pure metal atom, it must have gained an electron. So to go from here to here, it must gain an electron. Okay, so therefore, it has been reduced. Okay, and we show that by saying 2, okay, because we've got our 2 up here. 2 times, I've got the silver ion, because I've got 1 charge, or sorry, charge of positive 1, I just need 1 electron, and that is going to produce the silver metal. Okay, now if I compare that here to the zinc, so before the zinc was zinc solid, okay, after it becomes part of the ionic solution, which means that it is then the cation again, so zinc 2+ aqueous. Okay, so to go from here to here, it must lose electrons. More specifically, 2 electrons are lost. Okay, so that means that we're going to actually go to, so zinc solid breaks down to my zinc cation plus my 2 electrons here. I don't need the 2 in front because I only have 1 of these perfect things happening. I also have the nitrate ion. Okay, before the reaction, it's NO3 negative. After, it's NO3 negative. Therefore, oh, sorry. Therefore, we have no change. So it is a spectator. I should add here, since this lost electrons, this is oxidized. Okay. So, here we go. In that example problem, the zinc is replaced by the silver ions in the silver nitrate, resulting in the production of solid silver. This reaction is an example of a single replacement reaction. Since the nitrate ion did not change, the remaining ion in solution, it is called the spectator. So keep these terms in mind as you attempt the next practice questions. So a single replacement reaction is a reaction in which an element reacts with a compound to produce a new element and a new compound, and a spectator is an atom or a polyatomic ion that does not change in a chemical reaction. Now, redox reaction, as reduction and oxidization reactions, are the most common type of chemical reaction. In fact, the term reduction-oxidization reaction is used so frequently that it is often shortened just to redox reaction. So redox reaction is a reaction in which both reduction and oxidization take place. So, thank you very much for having watched this, and if you have any questions, be sure to jot them down so that we can deal with them tomorrow in class. Thanks for watching.